Good morning, everyone. My name is Venkatraja Ramalingam. I am from Geetham University. In this talk, we explore how the quantum fractal nature of the cosmic horizon modeled through the Barrow exponent interacts with an anisotropic Bianchi Type-V geometry to provide a robust mathematical bridge to the dark sector. Outline of my talk is that I will first discuss the observational motivation, like specifically the two crises that the Hubble tension and the CMB dipole anomaly. Then we will establish the uh, theoretical framework, which is Barrow entropy and the Bianchi Type-V geometry. Then I will combine the Barrow fractal entropy with an anisotropic Bianchi Type-V background. We will walk through the mathematical formulations, the equations, and including our formal reconstruction into the scalar field potentials like the quintessence. Finally, I will present our numerical results evaluated by the Python, and this evaluating the physical viability of the model through energy conditions and the Statefinder like or as diagnostics before concluding with our future research aims. Crisis in the standard cosmology and Lambda CDM model, that Hubble tension has the well-known discrepancy found by the Planck and the Shoes data, and they have the observations of about 67.4 and 73 by the last supernova as shoes measurements, local shoes measurement. And here the phi sigma discrepancy can be removed by the corrections because it needs the quantum gravitational corrections. And here we are also having the another crisis, the directional crisis given by the CMB. The observation like that the universe looks different in one specific direction. The specific data are given by the Secrist et al. Nathan Secrist et al. And they survey identify the CMB dipole tensions of 4.9 sigma in early 2021. And this is basically because of the 1998 observation by the local supernova as well as by the BAO and CMB measurements. We find that the universe is an accelerating universe, and these data sets give roughly the 95% of that is not known to our like matter particle. Only the 5%, that the 68.3% is the dark energy, and the 26.8% is the dark matter. This is given by this Planck 2018 data by the European Space Agency of the, and this is the total energy density of the universe. Hence, a dark energy is a repulsive force that permeates all of the space. And this is the means this is the dark component that is remain invisible, like the electromagnetic radiation will be detected. So this is not detected, and our research focuses on this 70% portion, that is dark energy, and specifically we investigate how the Barrow fractal geometry can explain its repulsive pressure in an anisotropic background. Here we see the Bianchi Type-V metric, which is the giving the solving this by the CMB dipole, which is created the observation imbalance in the CMB radiation. So one side of the sky looks slightly warm and the opposite side looks cooler because we are considering only the frame, rest frame. But in this case, the radiation and the matter rest frame is not coinciding. This is, I already told that the Secrist et al. And this from the MNRS data of 2025 recently. So we suggest it is an evidence of anisotropy. Uh, and the universe, this is evidence of anisotropy, and the universe expanded faster in one direction than another. Bianchi Type-V is an anisotropic model, and it is physically viable solution for the above anisotropy in direction, because it relaxes this account for the directional tensions observed in the modern cosmology. We focus on this Bianchi Type-V because it is open geometry. K is equal to -1 is more physically consistent with the late time acceleration required by the Barrow dark energy. The Barrow dark energy is that the boundary of the Hubble horizon. Unlike the closed Cantor C-Shax metric, which acts like a gravity, because this metric is also an anisotropic metric, which acts like a gravity fighting expansion. The negative curvature of the Bianchi Type-V helps push the universe apart. This is what we needed, and the Bianchi Type-V belongs to the model of non-zero structure constants. This mathematically forces the inclusion of the factor in the transverse directions, which represent the constant negative curvature of an open universe. Already I mentioned the K1 - 1 framework. In modern cosmology, we explore the several of the below for the cosmic acceleration, especially in the dark energy regime. And this is one is the cosmological constant, which is having the vacuum energy, empty space, and the dynamic scalar fields like the quintessence that change over time. And the holographic principle that we are investigating now is the energy derived from the boundary of the universe. Our research focuses on the Barrow Holographic Dark Energy, which incorporates the quantum-gravitational fractal corrections modeled by the Barrow exponent to the event horizon entropy, fractal-like deformation of the event horizon. That is, the Barrow exponent quantifies the quantum-gravitational deformation of the event horizon. Like when the Barrow exponent is 0, it requires the standard smooth, like Bekenstein-Hawking entropy. But when as the Barrow exponent approaches 0, 1, the horizon assumes a complex fractal-like topology that is very rough. This roughness creates an enhanced energy density, which we employ as the engine to drive the late time acceleration of our current model, that is Bianchi Type-V included the Barrow model. And it assumes the horizon is a fractal or fuzzy, and rather than the smooth. By adding this term, the math of expansion changes. The SB is equal to A by A naught. The A is the area of the event horizon, which is the 4 pi L square, and L is the IR cutoff. Go for this transition from geometry to the field equations. Here we have the line element of the Bianchi Type-V, and which is having the 3 directional scale factors, which are in different having the different Hubble factors of the respective directions. Because of the anisotropy, the instant tensor is we have derived it, and for our model. In this slide, the transition from geometry to the field equation, unlike the standard FLR metric, we move beyond the spherical symmetry to the account for the directional expansion. This is to allow the initial anisotropy of the universe's evolution. Coming to the energy density, the field equations after solving with the shear stress, the field equation provides the energy density constraint for our Barrow holographic dark energy model. It shows how the expansion rates, that is the in the different directions x, y, z, interact the spatial curvature to balance the total energy density of the Bianchi type, that there is a cosmic fluid. This minus 3 by a squared term in the energy density equation represent the Bianchi curvature term, where this the total energy density is the matter density and the Barrow Holographic Dark Energy density. Pressure, these field equations, we divide the spatial instant answer by the a square, and that is the P pressure, total pressure of the cosmic pressure is equal to the pressure of the matter and the pressure of the Barrow holographic dark energy. The spatial field equations acts as the dynamic engine driving the cosmic expansion, because here you see the evolutionary equation which shows the minus P total. Dividing by the a square allows us to project the geometry into the physical frame of the co-moving observer to measure the anti-gravity push. Here the spatial curvature term is 1 by a square for the open Bianchi Type-V. Consistency, co-moving consistency, to ensure our anisotropic model is physically viable. So we must satisfy the Z01 momentum constraint. This mathematically requires that the expansion equals the sum of the y and z expansions. Since because the universe with no flow in the x direction, therefore Z01 must be 0. This rule is fundamental to maintaining a stable co-moving framework, because we here equals, when the equation we are giving this G01 constraint, it equals H1 is equal to H1, H2 plus H3. This ensures the consistency of the Barrow dark energy model with the underlying spatial curvature B. This maintains the physical stability of the Bianchi type framework. In the IR cutoff selection, the Hubble horizon, the IR cutoff horizon L is equal to H inverse. Here the modified energy density by the Barrow holographic dark energy density is equal to CH square. We choose the Hubble length as our boundary because it avoids the causality and compatibility issues found in the particle horizon, because the omega is greater than minus 1 by 3. We are avoiding this non-accelerating regime. And many models using the particle horizon fail to reach the necessary acceleration threshold of that omega is less than minus 1.3. So our choice ensures the stability of the Bianchi Type-V solution. This also gives a thermodynamic consistency in an anisotropic background. Now going to the scalar field, we now perform a formal reconstruction by mapping our geometric Barrow holographic dark energy density to a dynamic scalar field sector. By setting these energy densities, that is the Barrow holographic dark energy equal to the density potential, that by adding the this is V5 is the quintessence potential. By setting the energy density and the pressures equal, we can translate the geometry into particle like quintessence to visualize the underlying energy potential. That is, we are equating the energy density of the geometric Barrow model to a dynamic scalar field to find the underlying physical potential. This formula actually, these two formulas actually defines the shape of the energy field that drives the acceleration shown in the we are generated the numerical results, and it shows this general framework provides a formal map for other non-canonical extensions, including quintessence and dilation models. Our results show that the Barrow exponent directly dictates the slope of the quintessence potential. The effective equation of state for the effective equation of state for the BHD is dynamical, and and varies with the time. Our numerical analysis currently places it in the phantom-like or quintessence-like region. That is, omega is less than minus 1, which is required to drive the acceleration. Now going to the other slide, that this is the strong energy conditions. This is violated. That violation of these conditions is a proof of the accelerated expansion. The persistent negative value throughout the redshift range. You can see here the in the negative region. So this is the physical primary requirement for the accelerative universe driven by the Barrow entropy. So to test the physical viability, we feed the effective energy density and pressure here in the y-axis, and this is to the strong energy condition formula. As the graph shows, the SCC remains persistently negative, less than 0 at late times. This is the energy input that proves our Barrow dark energy is providing the repulsive force necessary to drive the cosmic acceleration. Statefinder plot, we feed the higher order derivatives of the metric potentials of the A, B, and C. And by plotting S against R, we demonstrate that our model follows a unique dynamical trajectory. This proves our model is a geometric alternative that can be observationally distinguished from a simple cosmological constant. The Statefinders allows us to break the degeneracy that the Hubble and the deceleration parameters cannot resolve. While the Lambda CDM, as seeing in the lower portion, it is at the 1, 0 region here, and our BHDE model follows a unique trajectory in the RS plane. This proves our model is a unique dynamic solution to the Hubble tension. The Hubble evolution derived from our Bianchi Type-V field equations. We vary the Barrow exponent by to the 0.1 and 0.5 and 0.9, and that demonstrate the more fractal horizon surface, that when Barrow exponent going to 1, it can significantly shift the transition redshift, allowing the universe to accelerate earlier or later depending on the quantum corrections. As seen in this slide, our model shows a smooth transition from a decelerated phase when it is at the Q is greater than 0 in the past, to an accelerated phase, that is when the Q is less than 0, that is the negative regions. You can see this notices the dark energy takes over the model. That is, this is isotropization, means that the Hubble factors in the H and the A, X, Y, Z axis converge. This proves our model matches the universe we observe today. See here, this it proves this is the stable accelerating. This means this model reaches a stable accelerating FLRW phase right now. Solution. The study established the rigorous mathematical bridge between Barrow fractal geometry and the anisotropic expansion. We have shown that the fuzziness of the event horizon governed by the exponent Barrow exponent delta directly influences the cosmic potential and successfully drives the late time acceleration observed in our universe. Our model is physically stable and it satisfies all major energy conditions and provides a clear Statefinder that RS signature that can be tested by upcoming missions. This framework not only addresses the current Hubble tension but also offers a more generalized and realistic description of the dark sector, which is now most needed one, and it is then better than the standard isotropic models. I thank you for the opportunity given for me and at this time, and I